Hello, everyone, and today we start Chapter 3 on algorithms in discrete mathematics. So, first of all, what is an algorithm? And an algorithm is simply a finite set of precise instructions to solve usually a computational problem. Now, this is kind of a vague definition, but we'll get a little more precise in this definition as we move on. But for the moment, that's good enough. Now, an algorithm must have a number of properties. First one is that the input to the algorithm has to be from a specified set. It also needs to have an output that also comes from an equally clearly specified set. So the solution comes from this possible set of outputs. An algorithm is definite, so there's no ambiguity in any of the steps of the algorithm. Uh, for every possible input, it must give you correct output. It cannot work only sometimes, or 50%, or 90% of the times even. The number of steps that you have to perform to execute the algorithm has to be finite. Your algorithm, if you have an algorithm that can possibly, for some inputs, continue to run forever and never return a solution, then what you have is not an algorithm. So finiteness, this is an important property of an algorithm. Effectiveness of each calculation step, and finally, the generality for a class of problems. So you cannot have a set of steps to solve a specific problem. It has to apply to a wider class of problems. Algorithms can be described in many different ways. One of those ways is pseudocode, and I hope you did not skip the chapter on pseudocode in your first year course, CCCS122 Introduction to Computer Science. There are different ways of writing pseudocode. The one that's used in this textbook, in the textbook for this course, is according to the syntax that you'll see in the following slides. This syntax is similar to some of the early programming languages that we saw during the 80s, BASIC and Pascal. So here, as an example, here's the pseudocode for an algorithm that finds the largest element in a list of elements, in a list of n elements. So the algorithm is implemented in the form of a procedure. Procedure is, as you should probably know by now from your programming courses, means effectively the same thing as a function. Functions have names, and that's what we have right here. And then we have these round brackets, which means this is where we pass some kind of argument to this function, like in almost every programming language. And over here we have a list of n integers. So after the colon over here, this is specifying the type, the data type of these arguments a1, a2, all the way up to an. And simple enough, although there is one new thing on the next line over here. You'll see this strange looking symbol of a colon followed by an equal sign. This is basically how you write an assignment operator in this syntax of pseudocode. So all in C, in order to do this, what you would type in C languages, max equal to A1 semicolon. So that's basically that. This is an assignment operation happening over here, basically. Then we have a for loop that's self-explanatory, I think, given how much coding you've done up to this point. This is a for loop that runs from, it has a loop counter variable I, and that runs from 2 to n, where n is, of course, the number of the length of this array of integers that we're given as input, in which we're trying to find, in this algorithm, in which we're trying to find the largest of these values. And that largest value is going to go into this element max, initialized to the first element of the input array, A1. And so what happens inside the for loop, you simply check if the next element is greater than max or not. If it is greater, then you simply update the value of max with the new element that you compared it against. And by the time you come out of this algorithm completes running, max will contain the largest element of this array. Here's another example. This is what we call a linear search algorithm. And what it does is, over here we have as an input an integer x. Again, data type is given over here. And after semicolon, we have another set of inputs, an array of length n, consisting of elements a1, a2, a3, all the way up to an, also all integers. And what this algorithm does is it searches for the location of x in the array a1 through an. And we begin over here again, initializing variable I to 1. We have a while loop over here, and it'll continue as long as I stays within the range of indices that exist for the input values a1 through an, and it'll continue as long as the element ai that's being looked at is not equal to the element x that we're searching for. And while that is the case, if x is not equal to ai, I is incremented. Now, over here, the incrementation happens using this kind of traditional syntax of I equal to I plus 1, but occasionally you can also see the post-incrementation syntax that you're used to from C. You might see something, without the semicolon, of course, you might see something like that. And if at the end of it, if the value of the loop counter index I is still within the valid range, meaning between 1 and n, or less than or equal to n, then it means that location is equal to I. Otherwise, we set the value of this variable location to 0, meaning that x was not found in this array A. Those are the two possibilities. So either at the time we exit, we complete the algorithm, location will contain the subscript, the index of the term in array A that equals x, or it is 0, meaning that x was not found. Now, if the terms in an array are sorted, that affords us the option of using another search algorithm, a more efficient search algorithm. And this one's called the binary search algorithm. Now, the name binary means it has something to do with the number 2. So probably some kind of division by 2 or multiplication by 2. We'll see how that is appropriate here. And the binary search algorithm is much more efficient than the linear search algorithm that we just saw. However, like I said, it does require that the terms in which we are searching, that they are ordered. The basic idea is to not just look at, because the terms are ordered, the basic idea is to not having to look at every term in the sequence, but eliminate large portions of remaining terms that still need to be searched in each step of this algorithm. So for this one, let's move away from numbers for a minute, although, of course, you can absolutely use a binary search algorithm with numeric data types. But let's for a moment assume that we have a sequence, or we'll be given a sequence of letters, and we want to search for the letter J in that sequence. And here's a sequence of letters. It's not all of the letters of the alphabet, but as you can see, the letters that we have in this sequence are ordered alphabetically. If you had numbers, the numbers could be arranged either in ascending or descending order. And so the algorithm begins by setting a search interval, an interval on the data within which in this case, the letter that we're looking for, the element that we're searching for, in which that may lie. Initially, that letter, that search interval is the entire length of the input sequence. And so what we do is we jump to the center element. The center element over here being this element M. It's in the middle, between the start and end, in the middle of this interval. And we check, is M less than or greater than J? So if the letter that the element that we pointed at, if that is not the element that we're looking at, in the sequence, does it come after the letter that we're looking for or before it? Now, M in alphabetical order comes after J, which means that we know that J cannot be on this side, on this half of the sequence, which means we have immediately, without looking at them, we can eliminate all elements to the right of this element M, which means if J is anywhere, it is somewhere in this interval now. And this was one iteration of the binary search algorithm. From now onwards, we will repeat the same steps again and again until we either come up with nothing or we find the letter J. So, in the next step, we jump again to the center of the remaining search interval. That gets us to this element over here. Obviously, this element is the letter G. It is not the letter that we're looking for. It's not J. The question now is, does G come before J or after J in alphabetical order? And the answer, of course, is that G comes before J, which means that all elements, G included, all elements to the left of G and that leaves this as our search interval. We jump to the middle of that. Obviously, we have an even number over here, so we have to set a rule to either pick the left or the right element. So in this case, we're going with the floor function. We're picking the second element in the remaining search interval. And it turns out that by luck, this element is actually the letter that we're searching for. And keep going, and you end up with center element J. Okay, found. Okay. More generally, if you want to come up with if you want to write the pseudocode for the binary search algorithm, this is what we have over here. We have basically two pointers, one on the left side, one on the right side, and we keep moving one or the other. We keep moving them closer and closer together in this algorithm as long as they do not both point to the same element. As long as I is less than j. This is how we determine the middle element. It's basically the average of I and j. And then because the number of elements, the size of the search interval could be an even or odd number, we apply, as a rule over here, we apply the floor function to it to pick one of the two center elements. And if the element that you're searching for is to the right of the center element, then we move I to m plus 1. Otherwise, we move j to m. In the end, if index I, if pointer I, pointing at element AI, if that is equal to this element we're searching x, and we put into location the index I, the location of this element A, meaning that we found something. Otherwise, we're going to set location equal to 0, indicating that x was not found. Obviously, you have to perform many fewer steps in the binary search algorithm, which means that it is much more efficient than a linear search algorithm. The overhead, of course, or the prerequisite, is that the sequence already be sorted in ascending or descending order. And in this small example, it might seem like the binary search algorithm involved more thinking, more steps, more decision making. When you work on much bigger examples, just to give you an idea, in binary search, you're basically removing half the elements from further scrutiny in every step. Let's say you have a sequence that is 1024 elements long. In a simple linear search algorithm, you would have to look at every one of these 1024 elements. In a binary search, you can be done with your search in as little as log to the base 2 of 1024, which is simply 10 steps. So 10 steps versus something like 1024 steps. That is the difference between doing a binary search and doing a linear search. One is much more efficient than the other. And that brings us to another question. How can we analyze the efficiency of algorithms? We can measure running time, of course, which is the number of basic computations that have to be done. We can measure the efficiency of an algorithm in terms of space. which is the number of, or the amount of memory that it uses on a computer, or simply the number of variables that have to be maintained and that have to be maintained uh, while running the algorithm. So one is typically referred to as, then together they're referred to as computational complexity. The first one specifically time complexity. The second one is referred to as space complexity. And that brings us to the question, what is the time complexity of the linear search algorithm that we saw? Well, the worst case, and we always assume for these questions, we always assume the worst possible situation. And in the linear search algorithm, when you're searching for an element in a sequence, it's possible that you find the sequence at the very first element and you're done. But it's also possible that you find the element in the last element of the sequence. Obviously, finding an element in the last element is the worst possible case. And when we are assessing complexity of algorithms, we always assume the worst case. So if you have a sequence of n terms, the worst case is that the element that you're looking for using a linear search algorithm, the worst possibility perhaps is that the element is not in the sequence, which means you end up looking all the way to the end and not finding anything. Or maybe it is the last element, equally bad. Because in that case, you had to go through the entire sequence, every item of the sequence, in order to come to that conclusion. And you can see the pseudocode for the linear search algorithm again. You can see that we begin at index location 1, and after that it's basically up to the while loop to figure out when to stop. And that stop can come really early in the search, or it can come after we have gone through the entire sequence. So there are basically two comparisons. So within the while loop, there are basically two comparisons happening. There's this one over here. Is the value of I still within the boundaries of the array? And is the element pointed at by index I, AI, is that equal to the value we're searching for, x? So in each iteration of the while loop, we have to perform two comparisons, which means in the worst case, we have to do n iterations of the loop, which means overall, this algorithm may have to perform up to, or will have to perform up to 2n comparisons, 2 for each iteration. And you could, depending on whether you consider that an expensive operation, there's of course what happens inside the while loop. There's also the incrementation operation, it's an addition operation. Now, which operation we consider significant enough to count, which one not significant enough to count, depends on the architecture of the computer that you're using. Sometimes for some problems, we consider only multiplication as an operation of significant expense. That's usually the case in digital signal processing. For other problems, we may consider any operation, like even something like a comparison operation, which is usually considered inexpensive computationally. We may consider even that an operation, an incrementation operation, an addition operation. We may even consider that an operation worth counting. Outside the and after the while loop, there's another comparison happening in the if condition. If we check if uh, at what point we got out of the loop, out of the while loop, if it was at n or less than n, means we found something. In that case, we make an assignment. We copy the value of I into this variable location. So, which adds another operation, and we end up with 2n plus 2 operations over here. And then we had the binary search algorithm, and we can count the number of operations for that. So, what is the time complexity of binary search? So again, we'll assume the worst case, and let's assume that we have the number of elements is something to the power 2, kind of like what I just assumed, 1024 when I was talking a little earlier, which means that if I have n elements, which are a power of 2, in this case, let's assume the kth power of 2, then the binary search algorithm should run in worst case for up to k iterations. If you have a number of elements n that is not exactly a power of 2, so let's say n is somewhere between 2 to the power k and 2 to the power k plus 1, if it's anywhere in between, you can just assume for this purpose, you can just assume the number of elements to be 2 to the power k plus 1. So in the binary search algorithm, we of course also had a while loop over here. This one depending on this condition. So in each step, we are reducing the size of the search interval by half the elements in the remaining search interval. And we have one comparison operation happening over here. We have another comparison operation happening over here. So 2 operations in each iteration. All of this is being done assuming that doing simple math, assigning values, are operations that are not expensive enough or worthy of being counted. Okay. So, basic idea, I kind of gave it away. So basically, after you run through the while loop, you will have done 2 comparisons per iteration, meaning 2k comparisons. One, like I said, in the while loop condition, one in the if condition. And then there is another comparison coming out of the while loop. That gets us to a total of 2k plus 2 comparison operations in this algorithm. And k can be replaced here by log of n should actually be log to the base 2 of n with a ceiling function applied to it. Now, as long as the inputs to an algorithm are small, we're really not that bothered by time complexity or space complexity. So if you have small problems in which the input is, I don't know, maybe something like n equal to 10 elements, it won't matter much how efficient your algorithm is. But things start changing when the inputs grow to huge, humongous, gigantic sizes, something like 2 to the power 30, which is like a gig. So let me end it over here, and next time we'll get into the comparison of complexities of two algorithms, and there's a very solid way of how to compare algorithm complexity. We'll do that in our Sunday class. Thank you, and see you then.